right, this is section 11.5, square roots of variables. And so it's going to be a lot like the last section where you have to take something out of every pair under the square root, except you're going to have letters involved too, basically. So let's start, well, this is the main idea here, that if you have, here, if you have a pair of something under the square root, then one member of that pair will come out. Okay, so this would be a 2. And another way to write that, instead of saying 2 times 2, you could have it as a 4, but it's the same thing. Square root of 4 is 2, so a 2 would come out and it equals 2. Now we could do the same thing with variables. If I had a pair of x's, then one x will come out. And you'll have an x left behind. Or you could, instead of saying x times x, if you have an x squared, basically any kind of perfect square with a variable expression, the square, you just pull out the square root, which is x, and that piece is gone, so you get x. All right, so let's do some examples. Let's start with just the square root of 196y squared. Now the number part you're just going to treat like you would from the last section. So 196, if you didn't know, well, let's go ahead and do it this way. 196, I'm going to break it down. I think that's divisible by 4. Yeah. 4 and 49. Now both of those are perfect squares, so I'm going to leave it like that. And I'll have 4 times 49 and then the y squared. From the 4, I can pull out a 2 because that's the square root. From the 49, I can pull out a 7, so those are gone. And then from the y squared, he's a perfect square. Anything with an even exponent has a square root. So I would just take half of the exponent, so the square root is y. I'm gonna pull that out, and that's gone. And then these pieces that come out all get multiplied together and put in the front. Now there's nothing left under the square root. So in this case, we just get 2 times 7, which is 14y. And in your book, they have absolute value signs on some of the variables. We're not going to worry about that. We're just going to assume that all the values of the variables are positive, so don't worry about the absolute values. Okay, let's do square root of 36x to the 8th. Now, I don't really have to make a factor tree because 36 is a perfect square. So I could pull out a 6. And then anything with an even exponent, so even exponent variables are perfect squares. So you just divide exponent by 2. To get the square root. All right, so 8 is even, so then I know that's a perfect square. The square root, 8 divided by 2 is 4, so x to the 4th would be the square root. Those get multiplied together, thrown in the front, So there's nothing left over on the inside. So it's 6x to the 4th. Let's see. Let's do square root of 18 y to the 3rd. I don't know if you're going to have any of this type with an odd exponent in this section, but I'm going to give you one here just in case. So 18 will break down into a 2 times 9. That's prime, and that's a perfect square. So then I get 2 times 9, and then y cubed is not, 3 is not an even exponent, so y cubed by itself is not a perfect square. But if I take out, see, y cubed is y times y times y. So if I basically subtract 1 from the exponent, I can pull out one y here and call it y times y squared, right? That is y to the 3rd because the exponents would add. So that's going to give me a perfect square right here. So that's a perfect square, that's a perfect square. I can pull out a 3 from the 9. I can pull out a y from the y squared, and there's a 2 and a y that are still left over under the square root. These two guys get multiplied, thrown in the front. So 3y square root 2y would be the answer. Okay, I'm going to turn over now. Okay, example 4. Let's do square root of 28x squared. All right, 28 is not a perfect square. I'm going to go ahead and break it down. That's 4 times 7. 4 is a perfect square. 7 is prime. So I get 4 times 7 times x squared. I can pull out a 2 from the 4. The 7, it doesn't have a pair, so I have t stuck. X squared is a perfect square because I can divide, well, because x is the square root. Okay, multiply those together, put it in the front, and I get 2x times the square root of 7 is my answer. Okay, let's do 5 square root of 80 n to the 5th. Okay, so 80 I can break down to 8 times 10, that's 2 times 4, 2 times 5. All right. So I have 2 2s, a 4, which I'm just going to leave, and a 5. And then the n to the 5th is not, that's not an even exponent. So I'm going to take out one of the n's, and then there's 4 more left. So I'm just going to break the n to the 5th down, right? N to the 5th equals n times n to the 4th. So I'm kind of pulling this guy out of it. So that is a perfect square. I can pull out, now divide the 4 by 2. So n squared is the perfect square. He doesn't have a match. He's left over. He doesn't have a match. He's left over. I can pull out a 2 as the square root of 4. There's 2 2s. I can pull out 1. So these 3 pieces will all get multiplied together and put in the front. So 2 times 2 is 4. N squared in the front. The leftovers are 5n. And that's my answer. All right. If they put a negative here, which I think they might have some like that, it doesn't do anything. Just put a negative in your answer. And I think I'll do one more. We're already at 10 minutes here. Example 6. Maybe more than one of these. Okay, 45. This one's going to be a fraction underneath. 45 m to the third n squared divided by 5 m n to the fourth. So if you have something like this, first you want to simplify what's under here. So in other words, I'm taking the 45, it's kind of like those exponent canceling problems we did in a previous section. 5m n to the fourth. I can divide this by 5. I get a 9. I can cancel this m out of these 3. There's 2 left over on the top. And then there's 4 down here and 2 here. So I can cancel 2 out of this 4. So these 2 can cancel with 2 in this one. And I leave 2 behind. Or you can think of subtracting the exponents. 4 minus 2 leaves 2, but in the bottom. Make sure that stays in the bottom. All right, so really, this square root is just 9m squared over n squared. And whenever you have a square root of a fraction, you just do the square root of the top and the square root of the bottom separately. So that's going to give me 3m on the top, right? Because you can pull out a 3. You can pull out an m. And on the bottom, you can pull out an n. So 3m over n, nothing is left under the square root. And that's what you get. Okay. Actually, oops, sorry, one last one. This is going to be a long video. Example 7. X squared minus 6x plus 9. If there's pluses and minuses between them, you can't take the square roots of the individual pieces. That is not the same as x squared times 6x times 9. When you see this, it usually means you need to factor this expression. Now this is a perfect square because his square root is 3. His square root is x, 3x doubled, 6x. So, writing this as a perfect square, x, keep the first sign, minus 3 squared. Or if you were to factor it with trial and error, you would get x minus 3 times x minus 3. Either way, this has a square root. This is a perfect square. What comes out is x minus 3. And this is a pair, right? 2 things. So from any pair, you can pull out one member. You get x minus 3. So that would be your answer.